At the very edge of the universe, where space itself begins to twist and fold under the weight of endless gravity, there lies a final frontier, the last black hole. It's not just a cosmic heavyweight, it's the ultimate enforcer of the universe's final fate. Understanding this mysterious abyss could unlock answers about the lifespan of everything we know, and maybe even what comes after. Stick around, because what we're about to explore isn't just science. It's the ultimate story of existence itself. The nature of black holes and their formation. Black holes originate from the collapse of massive stars, especially those exceeding about 20 times the mass of our Sun. As these stars exhaust their nuclear fuel, they can no longer counteract gravity's relentless pull, causing their cores to compress intensely. This compression continues until a point of no return is reached, leading to the formation of a singularity, a point where density becomes infinite and our current understanding of physics breaks down. The collapsing star's outer layers often get expelled in a supernova explosion, but the core's gravity overwhelms these layers, pulling them inward and creating the dense, enigmatic object we recognize as a black hole. The process of black hole formation involves complex physics governed by Einstein's general theory of relativity. When a star's core collapses past a certain critical density, space-time itself becomes warped so severely that nothing, not even light, can escape. This event horizon marks the boundary beyond which escape velocity exceeds the speed of light. The formation is rapid. Once the critical threshold is crossed, the outer layers fall inward within moments, producing a black hole that can grow by accreting additional matter over time. Supermassive black holes, found at the centers of galaxies, likely form not only from stellar debris, but possibly through the merging of multiple black holes or direct collapse of large gas clouds. Interestingly, the nature of the matter inside a black hole remains a profound mystery. As matter becomes compressed into an infinitely dense point, the usual laws of physics merge into a singularity, where quantum mechanics and general relativity clash. This has led scientists to propose concepts like Hawking radiation, which predicts black holes can slowly evaporate over astronomical timescales by emitting particles. Still, the initial formation process, how collapsing matter transitions into a black hole, relies on the collapse reaching a density and temperature that defy straightforward description, reminding us of how much remains unknown in this extreme domain. Examples abound in the universe, from black holes formed by the deaths of massive stars to the supermassive black holes anchoring the centers of galaxies. The smallest black holes, often called stellar mass black holes, can be a few times the Sun's mass, while the supermassive counterparts can weigh billions of times more. Colliding black holes produce gravitational waves, ripples in space-time confirmed by LIGO, illustrating that their formation isn't just a localized event, but a cause of ripples across the cosmos. Every black hole is a window into the extremes of gravity and matter, continuously shaping our evolving understanding of how the universe's most mysterious entities come into existence. The concept of the event horizon and singularity. The event horizon functions as the boundary beyond which nothing can escape the gravitational pull of a black hole, not even light. It marks the point of no return. Once an object crosses this threshold, the escape velocity exceeds the speed of light, sealing its fate inward. The shape of the event horizon is influenced by the black hole's properties. For a non-rotating, spherical black hole, it resembles a perfect sphere, often called the Schwarzschild radius. In rotating or charged black holes, this boundary morphs into more complex shapes, like an oblate spheroid or warped regions. But the fundamental idea remains. It separates the universe's accessible realm from the interior, where classical physics break down. Inside this boundary lies the singularity, a region where density and gravitational forces become infinite. As matter collapses under its own gravity past the event horizon, the equations of general relativity predict that it concentrates into a point of infinite curvature, not a physical point in space, but a mathematical representation of spacetime's breakdown. All known laws of physics cease to operate meaningfully at the singularity. Although the concept is rooted in Einstein's equations, it challenges physicists because it suggests a boundary where our current understanding of physics cannot describe what happens. Still, Many researchers believe that a complete theory of quantum gravity could someday reconcile these contradictions. The relationship between the event horizon and singularity raises profound questions about the fabric of reality. The horizon essentially acts as a gatekeeper. Any information or matter crossing it is presumed to be lost to us forever, which leads to paradoxes like the black hole information loss problem. Some theories propose that information might be preserved in a holographic manner, encoded on the event horizon itself rather than lost at the singularity. Others explore the idea that the singularity might not be a true point of infinite density, but a region where the laws of physics are radically altered, potentially turning the concept into a kind of cosmic edge rather than a literal physical anomaly. Throughout scientific exploration, the event horizon and singularity serve as both boundaries and gateways, mysterious regions that challenge our understanding while offering insight into the most extreme conditions in nature. They exemplify how gravity operates at its most formidable, helping us glimpse the limits of our current theories and pushing us toward deeper, more comprehensive models of the universe. The dance between these two concepts remains one of the most compelling puzzles in astrophysics, capturing the imagination as scientists strive to unlock the secrets lurking within these cosmic enigmas. Theories on the end of matter and black hole evaporation. Black holes, especially the supermassive and evaporating varieties, have inspired countless theories about the ultimate fate of matter in the universe. According to classical physics, black holes serve as cosmic prisons, trapping everything that crosses their event horizons, including light. Yet, quantum mechanics introduces a twist. Stephen Hawking's groundbreaking idea suggests that black holes aren't entirely eternal. Instead, they emit radiation, now famously called Hawking radiation, which causes them to gradually lose mass and eventually evaporate completely. This process raises profound questions about what remains once a black hole vanishes. Does any trace of matter persist, or is it truly lost to the cosmos? The concept of black hole evaporation pushes the boundaries of understanding about matter's final moments. Some theories propose that as a black hole shrinks, the intense curvature of spacetime near its core breaks down classical descriptions, leading to exotic quantum phenomena. For instance, near the end of evaporation, the black hole's temperature skyrockets, theoretically releasing bursts of high-energy particles. This scenario suggests that the matter once trapped inside is re-emitted into space, possibly in a highly energetic and chaotic form. However, there's debate about whether this process conserves information or destroys it. The so-called information paradox pits quantum theory's principle of unitarity against the classical expectation that information swallowed by a black hole vanishes forever. Another fascinating hypothesis revolves around hypothetical Planck-scale remnants, sometimes called black hole remnants. These small, stable objects could potentially be the last observable traces of previously massive black holes. Proponents argue these remnants might prevent total disappearance, acting as reservoirs of matter or information. Critics, however, point out that these remnants could lead to paradoxes or violate established physical laws, making their existence speculative at best. Alternatively, some models suggest that the entire process of black hole evaporation might leave behind a firewall or a radically altered spacetime structure, radically rewriting notions of matters and state. In all cases, understanding black hole evaporation aims to reveal whether matter is truly obliterated, transformed, or if it undergoes some yet unconceived form of cosmic rebirth. Current research continues to probe these ideas, often through advanced theoretical frameworks like string theory, loop quantum gravity, and holography. These approaches attempt to unify the seemingly incompatible theories of quantum mechanics and general relativity, which underlie our grasp of black hole dynamics. While no definitive answer exists yet, the consensus is that black hole evaporation, in some form, profoundly influences the destiny of matter. Whether it dissolves into radiation, leaves behind remnants, or triggers new physics altogether remains one of the most compelling questions in cosmology and fundamental physics. Speculations on the final state of black holes and universal implications. Black holes have long fascinated scientists and the public alike, not only as cosmic phenomena, but as gateways to understanding the ultimate fate of matter and the universe itself. The traditional view posits that black holes, after shedding some mass via Hawking radiation, could eventually evaporate completely, leaving behind a paradoxical state, potentially a burst of thermal radiation that hints at a paradox between gravity and quantum mechanics. This evaporation process, however, raises profound questions about what remains when the black hole's mass dwindles to near zero. Some models suggest that the end might be a searing burst of energy, while others propose the formation of a remnant, a tiny, stable nugget of matter that defies complete decay. Speculation about the final state isn't purely theoretical anymore. It challenges core principles of physics and hints at the limits of our understanding of space, time, and information. For instance, the notion of black hole evaporation leads directly into the information paradox. If a black hole disappears entirely, what happens to the information about the matter that fell into it? Hawking's original calculations implied that this information would be lost forever, conflicting with quantum mechanics, which demands that information is conserved. This contradiction has sparked countless theories, from the existence of firewalls that destroy information at the event horizon, to the idea of information being encoded on the horizon itself, as suggested by holographic principles. Universal implications become ever more intriguing when considering what the final black hole might mean for cosmic evolution. If black holes evaporate completely, it could suggest a universe that cools and dilutes into a heat death, where all structures decay into a uniform radiation field. Conversely, some hypotheses propose that remnants of black holes, perhaps in the form of Planck-scale phenomena, could serve as seeds for new universes or hints of multiverse theories. Notably, the potential transformation of black holes into some form of exotic quantum state dissolves the boundary between destruction and rebirth, inviting speculation about whether the universe itself might undergo cycles of creation and dissolution governed by these ultimate black hole endpoints. Delving into specific models, physicists consider scenarios where the end state involves a stable remnant with a minimum mass, sometimes called a Planck mass relic, that survives after Hawking radiation ceases. These relics could potentially store all the information that fell into the black hole, preserving the laws of physics despite the black hole's disappearance. Yet, the nature of these remnants remains highly speculative, with ongoing debates about their stability and role in cosmic evolution. Ultimately, the mystery surrounding the final states of black holes underscores how much remains to be uncovered, each discovery reshaping our understanding of the universe's fate, and perhaps hinting at a deeper, more unified theory of reality. Usnovnoy, Rusgil 5. The concept of the final black hole as the ultimate endpoint of matter pushes the boundaries of contemporary astrophysics and theoretical physics alike. At its core, a black hole forms when a massive star exhausts its nuclear fuel and collapses under its own gravity, compressing matter into an incredibly dense point called a singularity. In this state, the known laws of physics break down, and gravity becomes so intense that not even light can escape. The singularity's density approaches infinity, where classical theories cease to describe what truly occurs, hinting at the necessity for an overarching quantum gravity theory. Delving deeper into the boundaries of this final point, black holes are believed to evaporate gradually through Hawking radiation, a quantum phenomenon where particle-antiparticle pairs near the event horizon result in loss of mass over immense periods. This evaporation process hints at a potential resolution to the paradox of information loss, revealing that what falls into a black hole might not be permanently lost after all. However, the endpoint of black hole evaporation remains shrouded in uncertainty, with some hypotheses suggesting complete disappearance, while others entertain the possibility of a remnant or a new form of exotic matter emerging at the brink of the singularity. The ultimate fate of matter within a black hole raises profound questions about the nature of existence itself. As the matter compresses into the singularity, its structure, if any, would be governed by yet-to-be-discovered quantum gravity principles. Some theorists propose that instead of a point of infinite density, matter could be compressed into a finite, extremely dense state, avoiding the paradoxical infinities that challenge our understanding. Alternatively, There could be a transformation into entirely different forms of matter or energy, possibly linked to the early universe's conditions or even giving rise to hypothetical phenomena like white holes or wormholes. In essence, the last stage of matter confronting a black hole seems to lead into a realm where conventional physics dissolves into possibilities. The black hole's final point acts as a bridge between the universe as we know it and a domain of phenomena that could redefine our understanding of reality. Whether matter ultimately ceases to exist, transforms, or gives way to other exotic entities, the study of black holes continues to push the frontier of human knowledge, hinting that the final point might not be an end, but an open threshold to entirely new physics. And so, we've journeyed to the edge of understanding, where matter bends into the ultimate point of existence, a place where the known laws of physics seem to break down and the fate of the universe hangs in the balance. We've explored how black holes serve as a gateway to the mysterious final stages of matter, pushing the boundaries of our knowledge and inviting us to reflect on the infinite complexity of the cosmos. If this peek into the universe's ultimate limits sparked your curiosity, stay tuned. There's much more to uncover in the depths of space and time. We'll be diving even deeper into these cosmic mysteries in future videos, exploring the frontiers of scientific discovery and the profound questions that challenge our understanding. Thanks for watching, and don't forget to subscribe and join us for the next exploration. They're just getting started.